I mean, I can if you want me to. I was just sticking to the order that we always do.
Somebody ate breakfast this morning.
Ooh,
Wow.
we could switch it up.
Okay, let's switch.
Mine's like hecka long, so.
Mine is not long. Okay.
It's good though.
It is good.
All right. Okay.
Okay. Hold on 1 second.
She's back again with the backgrounds.
Oh, that's very nice. Can I see that again real quick?
Yeah, I need to fix something. Okay.
Looks like it's supposed to be like graphene or graphite or something.
Yeah. I don't know. I thought it kind of looked like a cyclohexane, but in some
Yeah, it does look a little bit non-planar. So I don't know what the name is for like a sheet of fused cyclohexanes, but that probably is the thing. But what it really is like an artist's representation of what chemistry is. Like,
oh, yeah.
just to look chemistry-ish. Okay, the other thing I was going to do that I think we should do at some point is like take like a screenshot of like your group, but we don't have to do it today if people feel uncomfortable about their appearance. Okay, yeah. Okay, all right, Lindsay.
Okay, so I read a paper on the synthesis of islatravir, and it's like the first half of what Emily talked about. So it's like making the molecule that feeds into her biocatalytic pathway. And they just like basically wanted to find a different way to make the molecule. And they wanted to do this because most syntheses create a C4 stereocenter from a chiral pool of stereocenters or through enzymatic desymmetrization. And what they wanted to do is they wanted to find a different way to do it to create a more sophisticated intermediate that would feed into the enzymatic the biocatalytic pathway. And so, yeah. And then, so this is on the left here is the biocatalytic route that most syntheses use. And the first step is like the enzymatic desymmetrization. And just a note, compound 4, these two alcohol groups is actually supposed to be an aldehyde. It's just written as it's actually just shown as an aldehyde hydrate for some reason. We don't know why. And so this is the enzymatic desymmetrization, and then it's just the phosphorylation, which leads to compound 2. And compound 2 is kind of like the target molecule that they were trying to make, create another synthesis for to make this compound. And so on the right, this is what they did. And they started with this molecule instead of the alkyne already attached. And then they added the alkyne and then just phosphorylated it. And then this molecule, a compound molecule, is what feeds into the biocatalytic cascade. And so with their synthesis, they tried like a bunch of ligands to act as a catalyst to add this alkyne to here, and they found that L2, L3, and L4 worked, but AA worked the best, and this one did not work at all. And they basically grouped these L1, L2, L3, and L4 as chiral diols, and yeah, they just found that AA worked the best, and it was the most also selective with that. They like it had the highest enantiomeric excess.
So why do you think that some of the EEs are negative?
I was thinking it might be like it said that they used the chiral LC with a UV detector. Okay, never mind. That doesn't make any sense. I thought it might have to do something with that, but
anybody?
Can I try?
It's kind of an interesting thing. I've actually never seen that notation before. I mean, I think I know what they mean by that.
Is it like toward the unfavorable stereochem?
That would be my guess, is that like ligand 1 yes, gave a 50% EE of the wrong stereoisomer of 7.
Okay,
Yeah.
cool. And then they also found with the reaction is that there was like a background reaction in which compound 7 was reduced to compound 9. And what they found was that THF actually blocked that reduction. They don't really know why. Like I was trying to find a mechanism for it, but we don't know why. And you can see here like the ratio of 7 to 9 when it's just normally it's like pretty 1-to-1, and then when it's like lower temperature, it's a little bit better, but then when you add THF, you see this dramatic increase where it turns into a 20 ratio of compound 7 to 1, which you want compound 7 because you do not want it to be reduced. And then here is their overall synthesis. It's a bit long, but it starts with this molecule right here, and then the bromine is just a bromination, and then the benzoyl group is added, and the bromine acts as a leaving group. And then here, this is where they use ligand 8A and the THF. And what happens is the alkyne acts as a nucleophile, and then the electrons go up to the oxygen, and then the hydrogen, and then it acts as a nucleophile to take the hydrogen from a acid. And then this step right here is like the phosphorylation. This whole thing is like the phosphorylation, which is the second step that I talked about in like the first slide. And so what happens is they first deprotect it using base to get the TMS off of it. And then they do the selective phosphorylation with ethylchlorophosphate, which is the CPLO-OET2, to get this alcohol phosphorylated. And then they deprotect this the phosphate group and these methyls, and they use TMSBR, and they also use this methyl. It's 2-methyl-2-butene, which protects the alkyne from being brominated by the TMSBR byproduct, which is HBr.
Whoa.
And then yeah, it's pretty, and then also like this is like an acetal hydrolysis as well, is how they do that part. And
That's a really weird way to do that.
it is really weird to do that.
Yeah.
Yeah. And then this is the step that Emily covered yesterday with the 4 different enzymes and stuff. And then they also found another alternative pathway to their pathway that they found, in which they use the amber light resin, which I talked about last week, if you remember at all, which is basically used in place of an acid to protonate. And they do that to basically make these into alcohols. And then this compound 4, this is also supposed to be an aldehyde again. And then what they use is PANK and ACK, which are 2 enzymes, and ATP to selectively phosphorylate this alcohol. And yeah.
Nice.
Nice and short.
So it's kind of a nice way to I guess complement the biocatalytic route, and also some weird, I don't know, I guess a reaction you probably haven't seen before, which is an alkyne carbonyl addition. So that's the key reaction using zinc. Sort of like they don't really talk about it, but how the zinc works. But I sort of imagine that the alkyne, you make a carbon zinc bond with the alkyne carbon, and then that activates it to be like a nucleophile. It's kind of neat. I mean, it came up, I thought it was interesting because it like popped up on my radar because I follow all of these chemists on Twitter. And so this like popped up just like a week ago. So this paper isn't even really out. It isn't even really out yet. It's like in the like if you look at it, Lindsay, it's like for the date of publication, it's just like XXXX, you know. So it was just sort of funny that it happened. I don't know, just now.
Lindsay, I have a question.
Yeah.
I don't know if you know like, what this would mean, but what does it mean? Like, okay, so after like it's at the very bottom when they do like, what does co-immobilized mean?
I think I'm guessing it just means it uses the two enzymes to phosphorylate it. I'm not really sure. Scott?
Emily? You're muted.
Isn't that where that's with the protein bead, right? The co-immobilized? Does it have to do with that, Scott? So like the protein is attached to, or the enzyme is like attached to this bead that can be reused, like the enzyme is used and then another protein is able to attach to it and it's able to do its job, and like that, I remember talking about this, but
Yeah. It's sort of the same idea of that amberlite resin. Remember how like Lindsay brought up the amberlite resin is like a way you can have these functional groups attached to like a solid, like a bead. It's not like a big bead. It's like they're very small, but they're still filterable. And then so if you just chuck those beads in, you can like have the acid do a reaction and then you just filter it and then the acid is gone. They did the same thing with these enzymes, both of them. So they just attach them to a bead. They still work. Then they just like chuck the beads in. The reaction happens, and then you can filter the beads. And if they're lucky, they could even like wash them and reuse them like another time, or maybe another couple times.
So are these actual beads like physical? Like, oh, like when I think of a bead, that's what they're actually using.
Yeah, yeah. It's probably very, very small, but still filterable. Yeah.
Mm.
So
Is there a reason why they like? I feel like in everybody's like I guess topic, they've used some sort of beads to like measure something or like coat them with something.
yeah.
Is
Yeah,
there
it was
a
sort of
reason
like
for
in
that?
the alpha screen too. Like that's a bead based technique, right? Beads are nice because you can get rid of them easily by filtration, and that's probably the biggest advantage actually. And so they're just really easy to work with. So certainly in this case, I think that's why you would use like an amberlite bead or put enzymes on a bead. The other thing you can do sometimes that has also had beads was, let's see who did this. Oh, you did this, Naya, in one of your papers. Remember how I don't remember exactly what it was, but I think this was back like in the first one where they like had a bead or something, and it had, if I remember right, I think it had CRBN on it, and then, or no, it had Met AP2 on it, and then they attached the Protac to it, and then they took the beads and they added it to cells, and they wanted to see if when they filtered the bead, that CRBN or whatever that E3 ligase was back then, it had a different name. You know what I'm saying though, right?
Mm-hmm.
Did that come with the bead, which would mean that the IPP peptide, which was part of the Protac, bound to the E3 ligase? It would be evidence of that. You know what I mean? So beads are nice. Like they're just easy to isolate, and like you can wash them and use them to see if you can pull something with them, which would mean that would be evidence of binding. Yeah. Here it's just for ease, really.
Mm-hmm.
So you can filter something away and then have it just work. Have the process be junior high isable.
Hey, Scott, then what is the type of binding to the bead? Like, is it like peptide bonds, or how do these bind to the bead?
How do they stick them on the bead? There's probably different kinds of bead linker chemistry. Yeah. Sometimes the beads have epoxides, so anything that's nucleophilic will stick on the bead. So proteins could stick on a bead either through maybe nitrogens or maybe some alcohols or cysteines or something could stick there. Other beads have activated carboxylic acids. So if you add a protein to it, lysines, which end in amino groups, could make amides to the beads. I think there's a lot of choices for how the beads are set up to make covalent bonds to different things. So you could pick like whatever you want, whatever you think might work well for what you want them for.
Cool. Okay, thank you.
Mhm. Nice. Oof. All right. Any other questions? Great. All right, Beth, you ready? Okay.